This is our last example for this lecture number 4, and we have a coin now on a rotating table. The vertical direction is already described, so we know that the uh, gravitational acceleration is vertically downward. So it should be applied in this direction. There is our gravitational acceleration, and this rotating table starts moving from rest with a constant acceleration, angular acceleration of alpha, and we are asked to find the number of revolutions n through which the disk turns before the coin slips. So we understand that the coin doesn't slip, and the reason that the coin doesn't slip is because of the friction, and the information is given to us as the coefficient of static friction between the coin and the disk is μs. Now we're gonna apply a different approach here, because throughout this motion up to this n amount of rotations where the coin will flip, the acceleration in the normal and then the tangential, or as this is a fixed axis rotation, we can also use the r theta components, the polar coordinates. The components values will change throughout the motion, because at the initial case there is only alpha present, but then the velocity is equal to 0. So you can suggest that the acceleration in the normal direction is equal to 0 at that instant. In the tangential direction, it's not equal to 0. Therefore, the approach that we're going to follow is something like this. We're going to take a look at the magnitude of the forces will result in the change of the magnitude of the acceleration. Okay, so the magnitude of the acceleration will be dependent on the magnitude of the forces applied to this part. Now, the force we are talking about here, obviously, is on the horizontal case, because in the vertical direction, there's no motion of the coin in the vertical direction. It stays on top of the table. Therefore, the equation for that would be just, let me just call it Fz, would be equal to N is the normal force applied by the table to the coin, and minus mg is the gravitational force, and the motion, the resultant motion, is zero motion, no acceleration in that direction. Therefore, this m times 0, and we find out that n is equal to mg here. Now, the rest of the forces on the horizontal direction, however, we're going to make use of this strategy. That means I need to find out the accelerations at any given time for this coin. And I can use the NT coordinates, I can use the r theta components, whichever one you like to use. Let's use the r theta components, the polar coordinates, for this, as this is a fixed axis rotation. Now, in that sense, we're going to have an AR component and an A theta component. AR and A theta components will be, as this R is fixed, I'm going to write it out directly. I'm going to lose the part about R double dot, because R is a constant. So for AR, we're going to just have negative R theta dot squared. And then for A theta, again, we had a part about 2 times R dot theta dot. Now R is a constant, therefore I'm just going to lose that part. So what's going to remain is R theta double dot. Now theta double dot is given to us as alpha, and we can consider the theta dot as a omega, if you want, which is going to change throughout the motion, right? Because we have this alpha as a constant angular acceleration, omega will start from 0 and will approach to some value after n amount of rotations. Then the magnitude of the acceleration can be calculated as ar squared plus a theta squared. Let me just show it in a better way. So let's say this is the vector and we are trying to find the magnitude of that vector, the acceleration vector. Okay. So that's it. So we have the right side of the equation. On the left side of the equation, the only force acting on this coin on the horizontal plane is the friction force. And the friction force is nothing but mu s times mg, right? And is found to be mg. Remember that this is the maximum friction force, and I'm trying to use that maximum friction force. So you should be careful. In the beginning of this motion, the friction force is equal to almost 0, right? But then it has a constant acceleration, so there is some friction force. But then as it starts rotating and then the angular velocity becoming larger and larger, the magnitude of the acceleration becomes larger, friction force becomes larger. Up to which point? Up to the point where we're going to end up with the maximum friction force, and after that point on, the coin will start slipping. And the maximum friction force, so let me just show it here as FF max, can be calculated by making use of mu s and then n, and then we already discovered that n is equal to mg. So this is mu s times mg. This is the maximum friction force. So as a result of that, from this equation, we get this equality of mu s times mg is equal to m times the square root of ar squared plus a theta squared. Here we have the information about it. Mu s times mg is equal to m times ar a theta squared. There's the rewritten case for that, so there's a shuffling of the equations here, and as a result of that we get omega to the power 4 and alpha to the power 2. But then what we don't know about this is the omega. Alpha is known, but we don't have any information about omega. However, we can find the information of omega as a function of the alpha in this way, alpha and mu s. Now, the next thing that we need to do is we need to find out after what revolutions we're going to end up with this omega. So without the use of time, we have this third equation in our kinematics section. If you remember, A ds is equal to V dV, right? So that was our third equation in kinematics. And we don't include the time here. And it's very convenient for us because we are already looking for the amount of displacement. Now, here we need to change this equation for the rotational case, and here we have the equation for that. Omega d omega, these are the velocities, is equal to alpha times d theta. Now there's one more thing that we need to be careful about, is the relationship between the number of rotations and the total displacement, angular displacement. Now in one revolution we cover 2 pi radians of angular distance. So if you multiply 2 pi times n, this is the total angular displacement that has happened in the system. So here we have that knowledge as well. We have already written out this omega in this way as a function of alpha, and then if you do the necessary calculations of this equation, omega squared over 2. We have already find out the omega squared here. We're going to make use of that omega squared here. And instead of theta, now we can make use of this equation. So substitute 2 pi times n here, and then leave the n alone. And as a result of that, we find out the total number of revolutions at which the coin will start slipping. And that's the end of lecture number 4. We will start with lecture number 5 in the next video.